Electric current has various effects. We have already discussed heating effects of electric current in previous chapter. Also, we discussed chemical effects of electric current during process of electrolysis. In this chapter, we will discuss another very important effect of electric current, and that is magnetic effects of electric current. What is magnetism? The force of attraction or repulsion in and around a magnet is called magnetism. There are many naturally occurring magnets such as magnetite, an ore of iron. Also, magnets can be made artificially. A magnet has two poles, north and south. The north and the south pole of a magnet can never be separated. That is, monopoles do not exist in magnetism. Like poles attract each other, whereas unlike poles repel each other. The space or region around a magnet, or a current-carrying wire, within which its influence can be felt, or magnetic force can be felt, by another magnet is called magnetic field. The direction of magnetic field at a point is the direction of the resultant force acting on a hypothetical north pole, placed at that point. When a magnetic compass is brought close to a magnet, the needle is deflected. So, the space or region around a magnet within which a magnetic compass is deflected is known as the magnetic field of the magnet. Magnetic field is represented by magnetic field lines, or magnetic lines of force. It is the path taken by a unit north pole when placed in a magnetic field. Magnetic field induction or magnetic field strength, or simply, magnetic field is a vector quantity, as it has both magnitude as well as direction and obeys vector laws of addition. SI unit of magnetic field is Tesla, T. They are imaginary lines, drawn in such a way that, tangent to it at any point gives the direction of magnetic field at that point. Magnetic field's lines are directed from north pole to south pole outside the magnet. Inside the magnet, they are directed from south pole to north. Hence, magnetic field line is a closed and continuous curve. Degree of closeness of field lines represents relative strength of magnetic field. Magnetic field lines are crowded near the poles, where the magnetic field is strong. But they are far apart, near the middle of the magnet, and far from the magnet, where the magnetic field is weak. The magnetic field lines never intersect each other. Because if they do so, there would be two directions of magnetic field at that point, which is not possible. Uniform magnetic field. Magnetic field is said to be uniform if its magnitude is equal and direction is same at every point in the space. Uniform magnetic field is represented by equidistant, parallel, straight lines as shown in figure. Non-uniform magnetic field. Magnetic field is said to be non-uniform if its magnetic field is not equal and or direction is not same at every point in the space. Non-uniform magnetic field is represented as shown in figure. Magnetic field lines due to a magnet. Their pattern can be observed by sprinkling iron filings around a magnet. For this, fix a sheet of white paper on a drawing board using some adhesive material. Place a magnet in the center of it. Sprinkle some iron filings uniformly around the magnet using a salt sprinkler. Now tap the board gently. The iron filings arrange themselves in a pattern as shown in figure. Why? Because the magnet exerts its influence in the region surrounding it. Therefore, the iron filings experience a force. The force thus exerted makes iron filings to arrange in a pattern. The lines along which the iron filings align themselves represent magnetic field lines. Another way to draw magnetic field lines due to a magnet is with the help of compass. Place the compass near the north pole of the magnet. The south pole of the needle points towards the north pole of the magnet. The north pole of the compass is directed away from the north pole of the magnet. Mark the position of two ends of the needle. In this way, proceed step by step, till you reach the south pole of the magnet, as shown in figure. Hence Christian Ørsted established relationship between electricity and magnetism, and called it electromagnetism. Let's discuss Ørsted activity in brief. Take a long straight copper wire, 2 or 3 cells of 1.5 V each, and a plug key. Connect all of them in series as shown in figure. Place the straight wire parallel to and over a compass needle. Plug the key in the circuit. Observe the direction of deflection of the north pole of the needle. Now, replace the cell connections in the circuit. This would result in the change of the direction of current through the copper wire. You will see that now the needle moves in opposite direction. It means that the direction of magnetic field produced by the electric current is also reversed. Does the pattern of magnetic field lines depend on the shape of the conductor? We shall investigate this with an activity. We shall first consider the pattern of the magnetic field around a straight conductor carrying current. Take a battery, a variable resistance, or a rheostat, an ammeter, a plug key, connecting wires and a long straight thick copper wire. Insert the thick wire through the center, normal to the plane of a rectangular cardboard. Arrange the circuit as shown in the figure. Sprinkle some iron filings uniformly on the cardboard. Gently tap the cardboard a few times. You would find that the iron filings align themselves, showing a pattern of concentric circles around the copper wire. These concentric circles represent the magnetic field lines. How can the direction of the magnetic field be found? Place a compass at a point over a circle. Observe the direction of the needle. The direction of the north pole of the compass needle would give the direction of the field lines produced by the electric current through the straight wire at that point. A convenient way of finding the direction of magnetic field associated with a straight current carrying conductor is given by right-hand rule. Imagine that you are holding a current carrying straight conductor in your right hand, such that the thumb points towards the direction of current. Then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field, as shown in figure. A convenient way of finding the direction of magnetic field associated with a straight current carrying conductor is given by right-hand rule. Does the direction of magnetic field lines get reversed if the direction of current through the straight copper wire is reversed? Yes, it gets reversed. What happens to the deflection of the compass needle placed at a given point if the current in the copper wire is changed? To see this, vary the current in the wire. We find that the deflection in the needle also changes. In fact, if the current is increased, the deflection also increases. It indicates that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. What happens to the deflection of the needle if the compass is moved away from the copper wire but the current through the wire remains the same? To see this, now place the compass at a farther point from the conducting wire. We see that the deflection in the needle decreases. Thus, the magnetic field produced by a given current in the conductor decreases as the distance from it increases. From figure, it can be noticed that the concentric circles representing the magnetic field around a current carrying straight wire become larger and larger as we move away from it. Suppose this straight wire is bent in the form of a circular loop, and a current is passed through it. How would the magnetic field lines look like? Let's find it out with the help of an activity. Take a rectangular cardboard having 2 holes. Insert a circular coil, having large number of turns through them, normal to the plane of the cardboard. Connect the ends of the coil in series, with a battery, a key and a rheostat, as shown in figure. Sprinkle iron filings uniformly on the cardboard. Plug the key. Tap the cardboard gently a few times. Note the pattern of the iron filings that emerges on the cardboard. The observed pattern suggests that magnetic field lines due to current carrying circular coil near the coil are nearly circular and concentric. Near the center of the coil, the field lines are nearly straight and parallel. The direction of the magnetic field at the center is perpendicular to the plane of the coil. As we move towards the center of the coil, the strength of magnetic field increases. Magnetic field is maximum at its center. Magnitude of magnetic field, directly proportional to the current flowing through it, but inversely proportional to the radius, r, of the coil. However, it is directly proportional to the total number of turns. This is due to the reason that the current in all the circular turns of the coil is in the same direction. As such, the resultant magnetic field due to the coil is equal to the sum of the fields due to all these turns. A solenoid is a coil of many turns of an insulated copper wire closely wounded in the shape of helix, that is a tight spring. When an electric current flows through a solenoid, a magnetic field is set up which is similar to the magnetic field of a bar magnet and that of the Earth. Magnetic field lines inside a long solenoid are straight, parallel, crowded and equidistant, representing uniform and strong magnetic field. Magnetic field inside a long solenoid decreases as we move towards the ends of the solenoid because magnetic field lines near the ends of the solenoid start spreading out. Magnetic lines of force inside the solenoid are from south pole to north pole, and outside the solenoid, they are from north pole to south pole. Strength of magnetic field can be increased by increasing current through solenoid, increasing number of turns per unit length, introducing soft iron core in the solenoid. To find the direction of magnetic field due to solenoid, right-hand rule is used. Another convenient way to find the direction is, if the current flows in a clockwise direction, when the coil is seen end on, then that end of the solenoid acts as a south pole. On the other hand, if the current flows in anticlockwise direction when the coil is seen end on, then that end of the solenoid acts as a north pole. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material, like soft iron, when placed inside the coil to make electromagnets and permanent magnets. Electromagnets are formed when soft ferromagnetic substances, for example soft iron, is placed inside the current-carrying solenoid. Permanent magnets are formed when hard ferromagnetic substances, for example steel, is placed inside the current-carrying solenoid. Electromagnets are used in electric bell, circuit breaker, MRI, etc. We have learned that an electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on a magnet placed in the vicinity of the conductor. French scientist André-Marie Ampère suggested that the magnet must also exert an equal and opposite force on the current-carrying conductor. This force can be demonstrated with the help of an activity. Take a small aluminium rod, of about 5 centimeters. Using 2 connecting wires, suspend it horizontally from a stand, as shown in figure. Place a strong horseshoe magnet in such a way that the rod lies between the 2 poles with the magnetic field directed upwards. Connect the aluminium rod in series with a battery, a key and a rheostat. Now pass a current through the aluminium rod. It is observed that the rod is displaced. Why does the rod get displaced? Obviously, due to force acting on it. The direction of force, or motion, of a current-carrying conductor in a magnetic field is given by Fleming's left-hand rule. It states that, if we hold the thumb, forefinger and middle finger of the left hand mutually perpendicular to each other such that the forefinger points in the direction of magnetic field, the middle finger points in the direction of current, then the thumb shows the direction of force, motion, of the conductor. Force on a conductor, placed in magnetic field, is directly proportional to strength of magnetic field. It is directly proportional to the length of the conductor. It is also directly proportional to current through the conductor. Along with it, force is directly proportional to sine theta, where theta is angle between direction of magnetic field and electric current flowing through conductor. Hence, force is maximum when conductor is placed perpendicular to magnetic field. Whereas, when conductor is placed parallel to magnetic field, no force is experienced by it. Why does a current-carrying conductor experience a force when placed in a magnetic field? It is because of the interaction of the external magnetic field and magnetic field due to current-carrying conductor. Magnetic fields that are in the same direction make the combined fields stronger. Magnetic fields that are in opposite direction make the combined fields weaker. Hence, net force acts on it.
Working principle of DC motor. Working principle of DC motor is very simple. We can see that when the current conductor is placed in magnetic field, it experiences some force in particularly direction. The very basic construction of a DC motor contains a current-carrying armature, which is connected to the supply and through commutator segments and brushes. The armature is placed between north and south pole of a permanent or an electromagnet, in elementary model. One single turn of conductor is placed between two opposite poles. If we start to supply DC, via commutator system, current will start to flow. As we see, positive terminal of a battery is connected to left conductor of a turn, and negative terminal is connected to right conductor of a turn. As we see in model, north pole of the magnet is placed near left side, and south pole is placed near right side of the turn. Current in left side flows inward, and current in right side flows outward. As we see, conductor is carrying current and they placed in magnetic field. Both of them experienced mechanical force acted on them. Direction of mechanical force can be easily determined by applying Fleming's left-hand rule. To do this, spread out your left thumb, forefinger, and second finger so they are all at 90 degrees to one another. With that, if the forefinger is aligned along direction of magnetic field, from north pole to the south pole, and second finger is aligned along direction of the current and left side conductor, then thumb indicates direction of mechanical force. Similarly, if the forefinger is aligned along direction of magnetic field, from north pole to the south pole, and second finger is aligned along direction of the current and right side conductor, then thumb indicates direction of mechanical force. Due to this upward and downward forces on the turn, one torque is produced when turn rotates on clockwise direction as shown. After rotation of the turn comes to vertical position in respect of the magnetic field. At this position there is no current in conductor because conductor and brushes rest between two commutators. Hence, there is no force acting on conductor, due to moment of inertia, turn continue to rotates and comes horizontal again. Position of conductor has been changed here. That means conductor which was previously in left position comes to right position, and which was previously in right position comes to left position. At that position, we can determine mechanical force, with applying Fleming's left-hand rule. Let's do that. To do this, spread out your left thumb, forefinger, and second finger, so they are all at 90 degrees to one to another. So if forefinger is a line in direction of magnetic field, that is, from North Pole to South Pole, and second finger is aligned in direction of a current in the left side conductor, then thumb indicates direction of mechanical force. This is clearly upward here. So if forefinger is a line in direction of magnetic field, that is, from North Pole to South Pole, and second finger is aligned in direction of a current in the right side conductor, then thumb indicates direction of mechanical force. This is clearly downward here. Do this upward and downward forces, tends to rotate in clockwise direction. From that explanation we can come to conclusion that, here in this model we can see that, whichever conductor comes near South Pole, experience upward mechanical force, and near North Pole, downward mechanical force. And do this continuously forces, mechanical turn rotate, even if battery is not connected. Particularly DC motor, rotates, at the same principle like this elementary model. Instead of single turn in DC motor we have mountain turns on major coil. And instead of 2 poles there is number of poles, installed.